Hi, good afternoon. Okay. So today we're going to study two-dimensional compact surface and surface, we call the IUPUI orthogonal systems, three-dimensional space. Okay. So let's begin with the surface. Okay. When we say a surface is compact, more precise, we should say closed surface. Okay. So a compact surface can, it's possible can have a boundary. Okay. So in mathematics, when we say compact without the boundary, then means a closed surface. Okay. Closed surface means compact and without the boundary. Without boundary. Now, compact, how do you check compact? Surface compact, first of all, it's compact. Subset, second, it's a boundary, right? And this is compact. Well, it's closed in the sense of this closeness is about this, we describe this kind of surface, but not as a set, okay? A set is, a surface compact means, first of all, it is closed as a subset. Subset in R3. Second, it's also bounded, right? Then this as a subset, it's compact. Okay. Remember, a set is compact. A set in R3, right? A set in R3 is compact, means as a set, okay? As a subset. Okay. If one, this is a closed as a subset, right? Second, bounded. Okay. Now, closed it's not enough as a subset. For example, here's the example. Okay. This is the X, right? For example, X is R2 embedding in R3. Okay. And this is R2, right? X, Y, Z. And so this is a plane, right? And this is X. It's closed, okay? Closed means every sequence of points in the plane, if it's convergent, it's still converging to the point in the set, okay? This is a topological concept. But it's unbounded, so this is not a compact, okay? Some example, the first example. Second, this is X is not a compact set, subset, okay? Okay, and another one is going to call a sphere, okay? This is defined by the equation, x squared plus y squared plus z squared equals 1. Okay, this one as a subset, it's compact, means the remaining. That means R3 minus X is open, okay? It's open as a subset. So open means every point here, you can always find a small neighborhood such that it's contained in this set. It's obvious from the picture, right? As long as this point is not on the sphere, you can always draw the small ball, okay? So for any point not on the sphere, okay, then the ball with radius r is will not intersect with a set for sufficient small epsilon. Okay, so this is open set. That is why this is open. When it's open, then X is going to be closed by definition. And X is also bounded, right? X is bounded. X is bounded, clearly. Okay? Yeah. It is containing a bounded ball, right? So therefore, X is compact as a subset in R3. Okay. Now, when we say surface, a compact surface, if in general compact surface, it can have a boundary or has a no boundary. So the surface without boundary is called a closed surface. But that closed not means closed subset. As a surface is closed. Okay, so there's no open end. Okay, so this is for example, okay, the semisphere, x squared plus y squared plus z squared is equals to 1, and z squared then equal to 0. So this is this S. Okay. Now this S1 is compact. Okay, it's compact surface. Okay, with boundary. With boundary, the circle, right? See, the boundary is given by that notation. It's a compact set. So this is a compact surface with boundary. Okay, the sphere. This is epicenter. Okay, epicenter. So epicenter is a compact surface with boundary. Okay, we're not going to talk about compact subsets. Compact set. Okay, this compact means for the surface we have a definition, right? It's a compact. Compact means it's as a subset it's compact and also should be bounded. As a subset it's closed subset and it's bounded, or it's a compact subset. Okay. Now, in mathematics, yeah. Well, we have a very important theorem. Okay. Closed surface in R3. Okay. Any closed surface can be smoothly deformed to the following surface with G holes, right? So what does that mean? You can always you can always construct a surface okay. In this example, G equals 4. Okay. The sphere is a case G equals 0 because there's no hole here. Torus G equals 1. And you can put two torus together, glue two torus together, and right, you can cut a little bit this here, cut this here, glue them together, okay? So you can get a surface. This is about topology, okay? Surface looks like that with two holes. So in this case, G equals 2, okay? And it's guaranteed any surface can be smoothly deformed into one of such surface, any closed surface. If it's not closed, that's very complicated, okay? How about like this? Okay, let's here, I'm gonna have a ball. I put the two bars here, right? Okay, cut the two holes and I add the two bars. This is a closed surface. We can assume that's smooth, closeness. Okay, how many holes there? There's two holes. So actually you can deform the two about form. Okay. Why? You can shrink the ball. You can shrink a ball to step by step, right? You can, imagine, right? This is a steel ball, then this is a two ends like that, right? Okay. Then I shrink the ball to to tiny one. Right? This is my original ball, coming from here. Just shrink it. And then finally, you get, you get this. Okay. Those are the surfaces. Depends on how many bars on the ball. Yeah. You can imagine all the surface, any compact surface, closed surface in 3 dimensions. Yeah, in 3 dimension space, you can always deform it smoothly. Smoothly means it's not a, it's not, you're not going to break it. Okay, any other 2 points will be never touch it. Okay, so these 2 points here, they never touch it. It's maybe here, and maybe maybe here. Okay, they never connect. Okay. This is called every of them. This is diffeomorphism actually. You can smoothly deform means you can diffeomorphic to each other. They are geometrically they're different, okay, but topologically they're the same. Okay, so this is a topological theorem actually. Yeah, this is the topological theorem. Topology. Okay. In topology, we don't care how the shape of the surface. We only care the structure of the surface. Okay. So this ball with 2 hands, okay, with 2 handles, and it's topologically the same as like this 2 donuts connected together. Okay. But geometrically they're quite different. Okay. And the curvature somewhere is positive. Later we're going to introduce a curvature, and the curvature is quite different. When you deform it, the surface somewhere originally the curvature is positive, then it become negative. It's possible. Okay. Let's take a look at another example. You have a x squared plus y squared minus e to the 4th power equals 1. Okay. Let's look at this surface. Okay. So the surface, this is actually level surface, right? Level surface is defined by this equation. Okay. Well, is it defined for, you wanted to make sure this is defined for every x, x, y. So I'm going to put the negative sign here, negative sign, okay. All right, so first of all, it's a surface. How do you show that? Well, we let f to be x squared plus y squared minus e to the 4th power. So the gradient of this function is going to be 2x, 2y, and negative 4z cubed. Okay, and this in general is not going to be 0. If it's a 0, if and only if x, y, z is going to be the origin. Okay. However, okay, at any point x, y, z on the surface, right? This cannot be 0 or 0. Those components cannot be all 0 because it's 0 squared plus 0 squared minus 0 to the 4th power is going to be 0, so it does not satisfy the equation. So therefore, the gradient of this is going to be 0. So that means, okay, S is a smooth surface. Okay, even you can calculate the normal vector of the surface. Okay. Now, question is it a closed surface of the, is it closed or open? Okay. Is it closed or open surface? Okay. I'm not asking to check whether it's closed subset. This is as a subset in R3, it's closed, but as a surface, it's not closed. It's okay. So my claim is S is a closed subset in R3, but S is an open surface as a surface. Okay. Okay. Now, how do you see that? Why it's open? That means it's unbounded actually. Right? It's not. It's open. Yeah. Let's take a look at this equation again. So z to the fourth power is x squared plus y squared minus plus 1. Okay. It's unbounded. Okay. You can let x to be t, y to be 0. Okay. Then z is going to be the square root of, I choose a positive one, t squared plus 1. Okay. So you have a curve. To the fourth power. Right? Right? You can assume that t is greater than 0, right? T is greater than 0, less than infinity. Now I claim that this is a curve. This is a curve on the surface, but the distance from the origin, right? It's not necessarily from origin yet. Just the distance. Write it again. Yeah, the length. Okay, gamma t. Okay. This is the distance between the origin and the gamma t. Okay, and that is going to be squared. This will be this, and it clearly goes to infinity. Okay, so since this is on the surface, so the surface is this is unbounded. Okay, unbounded. So it cannot be compact as a subset. S is closed as a subset, but S is unbounded. So S is not compact as a subset. Okay. Okay. It does not have a boundary, but it's not compact. So let's open. This is open surface. Right. And how do you draw it? How do we draw the graph? Okay. So z to the fourth power, is going to be x squared plus y squared plus 1. So this is a graph. Okay. And there are two pieces here. Yeah, because z is going to be plus minus the fourth root of x squared plus y squared plus 1. I think it looks like, it looks like that, right? Other one is at bottom. It's harder to draw it. Yeah. That's two pieces. It's unbounded. It's going to infinity. This is a graph of each piece is a graph of function. The fourth root of x squared plus y squared plus 1. Right? All right, now I'm going to study the so-called 3-prime orthogonal of surfaces, right? It's three surfaces. It's a consistem of surfaces. The same. Before I talk about, I have to talk about how to say two surfaces are perpendicular. We consider two surfaces, okay? And they intersect here. So how do you talk about the angle between them? Okay. Right? Otherwise, you can talk about angle between at the point, then you cannot say that perpendicular to two surfaces, right? The idea is just look at the tangent plane. Okay, you have two tangent plane and the two tangent plane. Okay, so if you have two plane, right? How do you find the angle between them? I think when you try to find the angle, all you have to do is take a point, right? And draw the line perpendicular to that curve and draw the line perpendicular to that curve. This angle should be, the two angles actually, right? Depends on which angle is smaller. So this is the angle, okay? And this angle actually is the same angle as the angle between two normal vectors. Yeah. How do you see that? Okay, this is supposed to plane, and we're talking about this angle, right? And to calculate it, I cannot find the tangent plane. It's a waste of time, right? So what I'm trying to do is, how do I find this angle? How to calculate? This is a plane, right? This is plane 1, P1, P2. So P1, P2. I just simply write one line, two lines. Okay. All right, so now I use a normal vector n1, okay? Then I use another normal vector n2. And clearly this angle is the same as the other angle. So you can use a normal vector to find the angles, okay? Then you have to decide which side is a normal, which vector is normal vector. There's two choices there. Yeah, different choices give a different, yeah, maximum only two angles. Okay, now if you happen to be choose another one, okay, then you get the angle much larger, and that angle beta, right? And this is actually the angle, this one. Okay, so different choices, a normal vector, where we get two different angles. Right, but the sum of those two angles must be 180 degrees. That's only two possible angles, right? So this is a beta. Okay. So I have to do is just find the normal vector. Now using normal vector, so sometimes it's easy to find a normal vector if this is level surface. So consider two level surfaces. Okay. One is given by F. Other one given by G and KL, right? Right. So we assume that yeah, let X naught, Y naught, Z naught, V be an intersection point. So that means, so this is a surface. You know, right? Yeah, this is a G equals L. This is F equals K. I just showed two pieces, and here's my point. This is a point, right? This is a point P. Okay. So in order to find the angle between those two surfaces, all you just need to find the gradient. The gradient is going to be, right? So this is the L, F, right? So this is going to be gradient of normal vector, right? Right? Another vector G equals L. Okay, so G is actually pointed to that direction, gradient of G. So the angle between them is this theta. How do you find the theta? Cosine theta equals and they find the normal. Right? So this is how do we find the angle? So you use the two normal vectors. I just already explained to you use the two normal vectors. You can find the angle. Then you say orthogonal means you don't need to even normalize it. So yeah, perpendicular. These two surfaces, right? These two surfaces are perpendicular. If and only theta is 0, right? And if and only if H is the gradient of F, not the gradient of G. 0, okay? That's it. If along the intersection point, they all, this inner product is always 0, then these two surfaces are perpendicular along the intersection. Right? Right, so now let's take a look at examples. Okay. S1 is going to be x squared plus y squared equals z squared. But that one, yeah, here x, I assume that z is going to be positive, okay? So this is indeed a surface, S2. X squared plus y squared, z squared equals 1. How does that look like? That looks like, okay, and this is R squared in general, okay? So here's sphere, and this is a cone, okay? And then there's the intersection, circle, right? So I want to see whether what is the angle between the cone and the sphere at the intersection point. I think this is a constant angle, right? Yeah. Find the angle between S1 and S2 along the intersection curve. Yeah. This curve is called intersection curve. Remember, it's intersecting and curve, right? All right. So let's try to find out. I'm going to first of all, let's try to find the intersection, right? So look at the above two equations. Intersection means they're satisfying those two equations. Okay, here's the I is positive number. Okay, I is the radius of the sphere. Okay, how can I solve it? First, I find the z. I replace x squared plus y squared. Okay, so my z is going to be r squared over 2. Since z is always assumed positive, so it's r over square root 2. Okay, you determine z. X and y are not fully completely determined, right? But x squared plus y squared equals z squared, so it's going to be r squared over 2. So the intersection curve is defined by, in three-dimensional space, defined by x squared plus y squared, okay? And z is going to be r over square root 2. So it's a circle in the space. The radius here, capital I, is going to be r over square root 2. And there's a height is also as the height is r over square root 2. That's okay. Now I want to find at this point, and this is called the curve C. At the point x, y, z, at the point C, I'm going to find the normal vector of those two surfaces. And for the sphere, it's easy to find out. This is a sphere. I think I even don't need to waste time to find it. For the sphere, okay, for the sphere, right? All you have to do is just extend that direction. Let's get a normal vector. Okay, we have to normalize it. Okay, so it's going to be 1 over r. It's normal vector, right? X, y, z. This is unit vector. If you do not divide it by r, then it's just a vector perpendicular to the sphere. Okay, this is a sphere. The other one is a cone, actually. Okay, so so the function, okay, okay, how do I look at this cone? The normal vector cone. This should be the gradient of g, and then normalize, right? If you want to, yeah. G is wait, I didn't even mention g here, right? Did I mention? Yeah, g mentioned. Okay, yeah, g of x. X, y, z is going to be x squared plus y squared minus z squared. So the gradient of this is going to be 2x, 2y minus 2z. But the norm, okay, the norm is going to be 2 squared x squared plus y squared plus z squared. Now, since this is on the sphere, the point is on the sphere, 2r on the sphere, on the circle C, okay? The circle C is on the sphere, right? Okay, so you normalize it, and the cone is going to be divided by 2r, so it's the same. So the only difference is there's a negative sign here. All right, so now the inner product, right? The angle cosine theta is n sphere times n the cone, right? So I get 1 over r squared, and it has x squared plus y squared minus z squared. But again, this is a point on the sphere, x squared plus y squared equals z squared, right? So that's going to be 0. Okay. So that means the cone is always perpendicular to the sphere. So for this cone, right? So when you intersect with the sphere, when it intersects with the sphere, the angle here, okay, is always perpendicular, and that's easy to see from the two-dimensional case. Right. This is a 90 degree, I think, 90 degree. This is special cone. No, it's not, doesn't matter. It's not necessarily any arbitrary cone of this property. This is always no matter what it is. Okay? Even you have a smaller cone. Any line going through from the center, when it goes through the circle, okay, it's perpendicular to the circle. Well, we are interested in the system, orthogonal system of 3 surfaces. Okay. So here's the definition. Three families of surfaces. Okay. Form 3 prime orthogonal systems if one, exactly one surface of each family passes through each point of R3 or the same open set in R3. So that means have an open domain here. So that's U. Okay. Each surface in this family passes through each point, okay, in U, okay? So that means exactly, given every point, there is only one surface passing through this point, okay? So how can I say that? So each one surface, there are too many eaches here. Each family passes through each point P in U. Okay? in this open set. This is a 3 family of surfaces on U, okay, inside U, okay? We don't need the whole space. So every point, there's one surface in each family passing through that, okay? Those 3 surfaces here. All right, second, this key point. Any 2 surfaces, okay? Belong to different families or families, okay? Intersect orthogonally. Okay, so this is I think the second part is the most important part. Okay? This is required. Okay. So we have a family. Okay, say this family is a so this is a family. Okay, so UFG. You know, you can use a UFG, UVW, or doesn't matter. Okay. So 3 families of surface family. Okay, 3 family surface. One is XYZ equals let's call U, okay, for any fixed U. So this is family 1, okay? Another family is use capital V. It's defined by this. And the third one, W. So the first property says that I think the first property is automatically satisfied because UVW are the functions defined this open set. Okay. So at every point, you can always find a level surface passing through that point in each family. Now, what is important thing is they are perpendicular at an point. So what does that condition mean? Perpendicular means the gradient of a U at that particular point, and then it's perpendicular, okay? So that should be 0, right? Perpendicular, right? Also, there's also was another vector, another normal vector, right? It's 0. Then I think one more. These 2 surfaces also should be perpendicular. Okay. So there's 3 conditions here. I'm going to consider a map. Okay, consider the map. And this map is constructed by F is U into R3, okay, and defined by the following formula. So this family of level surfaces, you can use that to define the 3 functions. You can define map. Okay, what does that mean? This is this. Okay, the first property is F is defined on the whole U, right? This is so every point there's one surface passing through the point. I think the second one, let's look at this map. Right? Let's look at the Jacobian of this map. Jacobian of this map how do we define it? This is the partial derivatives. Okay. I think it can be defined like this: ux, vx, wx, uy, vy, wy, and uz, vz, wz. Okay. So my based on what we assume, the assumption, we are going to get non-degenerate matrix. My claim is the determinant is not going to be zero. Why this is obvious? Think about it. Yeah, I forgot to mention that at the very beginning. Yeah, this is system surfaces belong to the so we can see the the three level surfaces, right? Okay, and we assume that at any point we have to assume that the gradient u, okay, is not going to be zero. The gradient of v is not going to be zero. The gradient of w is not going to be zero. So you get three smooth surfaces. Okay, so they are smooth surfaces, but they also in addition they satisfy those three conditions. Okay, so we assume that, right? We assume that this set and that. Okay, so with these properties, right? Okay, this the norm of a gradient u is not going to zero guaranteed. U equals the little u, right? It's a smooth surface. Now, how do we see? This is a how do we see this is a it's as a determinant is not going to be zero. So I can even show you what is determinant. So what I'm going to do is it's linear algebra, okay, times the transpose of that, okay. So it's ux, vx, wx, uy, vy, wy, uz, vz, wz, and the transpose is going to be ux, uy, uz. Okay. Okay. Vx, vy, vz, wx, wy, wz. Okay, let's multiply them out. The first one is just the gradient u squared. Right? The second is 0, 0, 0, 0. Okay, so that is that's great. You know, when you this low times that column, when this low times that column, it's going to be 0. Okay, when this low times that column, the first row times the second column is 0. Only the first row times the first column, you get the square of the norm, the length of the gradient u. Okay. So the determinant of GF, okay, is going to be this is not going to be 0. But from linear algebra, the determinant of the product of the two matches is going to be, okay? But the determinant transpose of this Jacobian itself. Okay? So you will get square. Okay? The determinant square. This is a wow. So this map you have this. That's why it's going to be. By our assumption, our surface, right? So this map, F right now, okay, it's used into R3, okay? And 1, F is 1 to 1. Why? Because we assume that the surface, each point, there's one particular point of the surface from passing through this point. So that's from assumption of, second, the determinant of Jacobi is not going to be 0. Okay? So that implies F is a diffeomorphism. Okay? Into a set U bar of the image to that set. So you get a diffeomorphism. It's nice diffeomorphism. So this is how do we get diffeomorphism. Okay. All right. So you may able to find, sometimes you can find the inverse, okay? Sometimes you can find, okay? F, X, Y, Z is going to be U and V, W, okay? Then X and Y, Z is going to be the inverse of U and W. Yeah, sometimes you can find the inverse, but sometimes you can only say, okay, by the mathematical theory, you know. So if the Jacobi is not in 0, if it's 1 to 1, and if it's not 1 to 1, then you can only say locally diffeomorphism. You cannot say group. All right, so that's what we have here. Okay, and we hope we can, in some examples, we can find UV, right? So we consider, I'm going to consider 3 examples. Okay, U, X, Y, Z. It's going to be X squared plus Y squared plus Z squared. V, X, Y. This is going to be X squared plus Y squared minus Z squared. Okay. I need another one, right? Right, the third one, it's a plane. Okay, this is a sphere. I have a family of a sphere here, right? So I have the cone. Right? This is determined by V equals little v. And this is the V equals 0, special case. This is sphere the U equals R, right? I can construct the third one. Third one just x minus x divided by, yeah. I just look at this planes passing through them. So x divided by 1, okay? Right, so u equals little u means it's a sphere. Okay? V equals little v. It's not necessarily cone, but it's a parabolic. No, not exactly, right? What's the name of it, right? So that means z is going to be x squared plus y squared minus v. So this, it depends on value of v. Okay? If v is positive, that's how does it look like? X, y, z. If v is positive, it looks like that. If v is positive, okay? And the x, y, cannot be too small. W equals little w. So that means x of y equals w. So you get plane and this is a plane, okay, passing through the origin. Okay, so this is a plane. Right? And maybe I change y over x. Make it easier. Yeah, let me give it a change. Y over x is y over x. So y equals w x. Okay, w is a slit. Okay. Now my question: do they form the three-prime orthogonal system? Okay. We already showed that the gradient. Yeah, let's look at the gradient of u. Okay, the gradient of u is going to be 2x, 2y, 2z. The gradient of v is 2x, 2y minus 2z, I guess. The gradient of that is going to be y over x squared, and this is 1 over x, right? That's going to be 0. Okay. Yeah, let's look at the inner product. This is going to be 4x squared plus y squared minus z squared, and that is going to be 0. I think the construction I get here is I need to modify it, because otherwise this is true only when v is a little bit 0. How can I modify the v? How do I modify the v here? I'm going to I think yeah, this is you see, because when capital V equals 0, then x squared plus y squared minus z squared is 0. Otherwise, it's not going to be always perpendicular. Okay. So we needed to modify. Okay, this is not working. So I want to look at the cone containing the x-axis. So in that case, yeah, let's try a different one. Okay, that's not working. I'm going to y squared plus v squared minus x squared. And then I put the constant v here. The family of a cone. How can I describe this? Yeah, I can do this one. It's not it does not. Okay, this is going to be x squared plus y squared minus z squared. Okay. So the level surface of a V is going to be the cone, family of cone. Okay. So now, when V equals, yeah, I need to change this. Okay. So this is x squared plus y squared plus z squared equals u. And this is going to be x squared plus y squared equals vz. Okay, squared. This is going to be y equals w. Okay. So so I needed to modify. Otherwise, I'm not going to get that. This is not always true. I hope this time it works. Okay. So I get the gradient of x squared plus y equals this squared. The gradient of this 2x z squared to differentiate with respect to y. 2y z squared. Then, okay, then I have x squared plus y squared z cubed over 2. Okay. Yeah, because z to the negative 2 when differential is negative 2, right? I hope this time it will work. Okay. Let's try this. Otherwise, we'll get it. Okay. Okay. So when I look at the product, okay, I get z squared twice of x squared plus y squared. And the minus, when I have a z here, yeah. So that would be 2 2 to 4. Vx squared plus y squared. Great, it's real. Okay. Okay. How about this? This is a product. It's 2x negative y over x squared and 2y times x. Wow, this is also 0. Great. And now the last one. Okay, the last one. And that's going to be the product 2x over z squared and negative y over x squared and plus 2y over z squared times 1 over x. Okay, wow, this is also 0. Great, so we do get we do get you know, this is called the orthogonal system. Okay. So the level, let's take a look at this level surface of U and V. U equals, this is going to be a family of a sphere with radius square U. And capital V equals little v is going to be a family of cones, right? And they are all start from the origin. This can be shrink and expand. And this is it's a family of a plane. Okay, y equals wx is a line in the xy plane with slope of w. But this line, because there is no restriction on this, so actually is a plane in the three-dimensional space. Wow. So think about our map F. Okay, think about our map U, V, W. Okay. So what is U? U is x capital U, right? And this x squared plus y squared, z squared. And this is y of x. Okay. Okay. It's defined on the domain. We assume that these are positive. Okay. I can also assume that this x is not zero, so x is also positive. So the domain we have here, this positive, x is positive. So we're talking about this area. Okay, this whole region. Okay. So this is our U. And then the image is the image is harder to describe it. Okay. At least the U is positive, right? V and the W. And V is positive. V is positive, right? W can be any number. So probably this is the region we're talking about. Yeah, V is positive. V is positive. W can be negative, can be positive. Okay. So this is a map. It's a diffeomorphism. And we get diffeomorphism, right? Are we able to solve it? The inverse. Okay. X, Y, Z equals U, V, W, right? I'm going to, yeah, there's U is positive, V is positive, and W is the arbitrary number. I'm going to solve it. Okay. So I hope I can solve it. Maybe not. U, right? U is positive. And x squared plus y squared equals V, Z squared. V is positive. Then here's a y over x. W, it's arbitrary number. So for given UV, and we try to find xy. Are we able to find it? And here, I think my x is Zx is positive, Z is positive. We assume that, right? X is positive, Z is positive. W is just arbitrary number. And I'm trying to. Okay, from here, right? So V, Z square plus Z square is going to be U. So Z square equals U, V plus 1, great. Okay, our Z is positive, so Z is, okay, great. So you find the Z. Once you find the Z, you get x squared plus y squared, right? By the second equation. U and the V plus 1. So U, V plus 1. But on the other hand, y equals wx, so you can put it here. So x squared w squared x squared equals uv v plus 1. So x squared is going to be uv v plus 1. Now, do I assume x is positive? Yes, that's why I have to assume x is positive. uv and the v plus 1, and I think, yes. Okay, we are very lucky, you know, we got all of them. Okay, let me write down this. Okay, x is going to be uv v plus 1 and w squared plus 1. And the y is wx, so w. Okay, and the z. What is my z? Z already got it? Yeah, we already got it. Z is the square root of u over v plus 1. Okay, so this is the inverse. This gives you the inverse of the map. Okay, this define. Okay. So now you have a map in three-dimensional space using this family of using those three family of surfaces. Right. So this is an interesting map. Right. Transformation is very interesting. You can deform the picture in three-dimensional space to another bit using this. You can write a program. Okay. A nice ball here, you know, a nice whatever picture, right? So in this three-dimensional space, under the transformation, diffeomorphism, right? And it's harder to imagine how does it look like. Okay, you know, only use a computer, maybe you can see that. Maybe it looks like that. It's very special, you know. Okay, so it's harder to describe. I understand. Okay, so you can use the mathematics. You can deform picture. You write down using this those functions. Okay, using these functions, you can deform. Yeah, so we already got f in universe, right? And this is f. Okay, that's forward, backward. Right, so if you live in a two different world, and this is a picture you can see here in this world, and then there's a picture in another one that looks completely different. Okay, beautiful things here does not mean beautiful things over there. Right, sometimes you look at a mirror, right? You know, in some museum or some other place. Okay, science museum, right? And the kids look at the mirror in front of them. This kind of transformation here, that looks very funny face, and then there's a laughing, right? So you can see that the same object, but transferred into a different space that look quite different, very funny sometimes. Okay. So I stop here, and we use three families of orthogonal surfaces. We actually get nice special transformation, diffeomorphism in three-dimensional space.